in chapter 3, we're moving on to a bunch of rules on taking the derivatives. And what we're doing today is derivatives of polynomials and exponential functions, also known as the shortcuts. So no longer will we ever have to do the limit definition of the derivative. It is important that you see where that comes from, that approximating slope of the secant line. But what I'm going to do is today show you how to find the derivative of polynomial and exponential function without that limit definition. And we'll be able to do it in about that quick. So good news. So the first one is just the derivative of a constant. So if we have f of x is equal to c, just some constant number. So for example, f of x is equal to 3 or f of x is equal to -2. Oh man, I'm so excited about the iPad. I'll be able to just like hit the ruler and come up with lines really quickly. I'm going to practice and give it a try for you guys next week sometime. So here's 3, here's -2. So I'll color code these for you guys. In the chat box, help me out with this one once you get this down. Remember what the derivative means is the derivative is the instantaneous slope at a point, or it's the slope of the tangent line, and we use that limit definition with the approximating secant line. So the translation you should think of in your head is slope of the tangent. So if we look at both of these constants, what is the slope in either case? What is the slope in either case? Yeah, 0, okay? So it turns out the derivative of a constant is always 0. So for any f of x equals any constant, it doesn't matter what the constant is, f prime of x is always equal to 0. The other way we write this is d dx. This is our differentiation operator. So the derivative of a constant is equal to 0. Okay, so these two things, here's our first statement, right? If our function is a constant, the derivative is 0. Here's saying the derivative of a constant is 0. If we wanted to do the proof, this is super easy. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So in these two cases, f of x plus h and f of x, since this is a constant, we have c in both places. And this is just 0. Any questions so far? Okay, so derivative of a constant is 0. You should memorize that. The next one is the most useful one, and now you're going to wish that you could go back to the 2.7 homework and do it with the shortcuts. So the next thing we have is called the power rule, and this is going to help us find derivatives of polynomials. Okay, so the power rule says let n be a positive integer. If f of x is equal to x to the n, so a monomial, a polynomial with only one term, monomial, then f prime of x is equal to n times x to the n minus 1. In other words, the derivative of x to the n is equal to n times x to the n minus 1. I'll put up the proof really quickly. You don't have to write this down in your notes if you don't want to, but it's important in math, you know, that you don't just blindly trust everything I tell you. So if you want to read this, follow along, cool. If you don't want to copy it all down, that's just fine. So if we wanted to compute the derivative of x to the n, We start with our derivative definition. The limit as h goes to 0 of f of x plus h minus f of x over h. This problem looks exactly the same way as all of the homework problems from section 2.7. The next thing we do is we evaluate these two expressions in the numerator. Then remember, our next step was to multiply out the numerator and cancel out a bunch of terms. So if we multiply out x plus h to the n, we get x to the n plus n times x to the n minus 1h plus dot, dot, dot. All of these terms have higher powers of h. And then minus this x to the n on the end. All over h. Okay, so then the next thing we do, just like all of our homework on section 2.7, cancel out any common terms. So we can see that these common terms cancel. Then the next step is we divide by h. So we have the limit as h goes to 0, in x to the n minus 1 h divided by h is in x to the n minus 1 h. And then the h's cancel, right? H's cancel. And then all the rest of the terms are going to have h in them. Now what happens as h goes to 0? Any of these terms that have h in them, h times anything is 0. So that's just going to give us x to the n minus 1. So there's our proof. We haven't talked about this yet, but in math, at the end of proofs, you'll either see one of two things. Usually there's either a square that indicates the proof is done, or you see QED at the end of a proof. So if you ever see those at the end of math proof, this stands for quid erat demonstratum. What was meant to be shown has been demonstrated, quid erat demonstratum. So you might see either of those two things. And as a math person, when you do a proof, it's kind of like satisfying, right, to put QED at the end or a little square, like nailed it. So anyway, I won't ask you to repeat these proofs, but I just want you to see where this formula comes from. So what we'll do next is we will do a bunch of problems using the power rule, and you will thank me and wish that you could go back to the 2.7 homework and do it really, really quickly now. And I apologize for making everybody do it the long way. It's an important exercise. Anybody need more time on this page? Okay. You don't have to copy down this proof if you don't want to. But like I said, my goal is hopefully by next week I'll be up and running with the iPad, and then when I'm done with lecture, I can save my handwritten notes and just like email that file off to you guys really quickly or post it on Canvas or something. So that's what I'm working on for you. And I'm technologically, I don't know what the right word is. I have an iPhone 6. I have an iPod Shuffle. I always get made fun of for that. And this is my first iPad, so it's kind of a lot to figure out. My kid, though, I'll tell you what, my 7-year-old kid, he knows how to work. He has like a Kindle or something. He'll be like, boop, 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 boop. He knows all these things. And I'm like, okay, Blake, do this for me. So, all right, I'm gonna go ahead and move on. If you need me to put this back up later, I certainly can do that. So let's do some examples using the power rule. And I'll do some examples in different notation here. So our first function, let's say we have f of x is equal to x to the 7. Now, thinking about how we did this in section 2.7, we would set up the limit definition, and now we have to multiply out x plus h to the 7. That's horrible. So let's not do that. From now on, what we're going to do is use the power rule. The power rule says if we have x to the n, then what we do to find the derivative, we bring the power down in front. So we write this as 7x, and we decrease our exponent by 1. That's it. That quick. Let's do some more, and I'll do some different notation here. So if y is equal to x to the 649th, okay, then y prime, right? F prime of x, y prime, this is different notation for the derivative. They mean the same thing. The power rule says all we do is we take the power, we move it down in front, and we decrease our power by 1. That's it. Let's do some with some other notation. How about the derivative? So when we see this d dx here, this is our differentiation operator. This says find the derivative. So find the derivative of x to the 12th. Our power rule says we bring our power down in front, and then we decrease our exponent by 1. That's it. All right. How about in the chat box now, I'll have you guys give one a try. How about d dt? So now we're taking the derivative with respect to t of t cubed. All right, in the chat box, tell me using whatever shortcut notation you want, what do you think the derivative of t cubed is? Yeah, 3t squared, great. Okay, so how easy is that compared to what we did in section 2.7? So, and I had mentioned to you last week that I didn't put 2.7 on the exam because those of you who have already taken calculus know the shortcuts, and it wouldn't have been fair for those of you who didn't take calculus to go through that horrible, I shouldn't say horrible, let's say lengthy limit definition. Okay, so now we can do these quickly. All right, I got a couple that are a little bit more difficult that you might have to think about. How about, what is the derivative with respect to x of x? What do you guys think the derivative of just plain old x is? Okay, this one's a little bit tricky. So what you want to think about is this is x to the first power. Okay, x to the first power. So our power rule works in exactly the same way. We bring the 1 down in front, we write our x, and we decrease our exponent by 1. So now we have 1 times x to the 0. Anything to the 0th power is 1, right? So now we have 1 times 1, which is 1. The other way of thinking about this is just thinking about literally what this is. This is a line, right? Looks like that, a line with slope 1. So anywhere the slope is 1. Okay, so either way. So you should know that the derivative of x is just 1. All right, I got a harder one for you. Oh no, I already put this up on the last page. Just kidding. I got an easier one for you. How about the derivative of just 3? It's just 0. Okay, so the derivative of a constant is 0. The power rule sort of works here. You can picture this as 3 times x to the 0th power. We bring down the 0 in front, and 0 times anything is 0. So you can kind of picture that this is 3 times x to the 0th power, bring the 0 down in front, 0 times anything is 0. Good to go. Any questions on this? Now, our proof on the last page said that the power rule was for positive integers, but it also works for any other power. However, the proof is not the same. So the proof was for a polynomial expression, but the power rule extends to non-positive powers as well, and also it's not to integers. So let's look at a couple other examples. So how about if f of x is equal to 1 over x squared, how do we find the derivative? Okay, the first thing I'd like to do is refresh your memory that anytime we have an exponent in the denominator, we can rewrite this as x to the -2. Remember, anytime we move something between the numerator and denominator, the sign changes. Okay, so now that we have this in kind of the standard form, then what we do is to find the derivative, f prime of x. We can still use the power rule. The proof just only applies to polynomials. So we bring the -2 down in front, and then we decrease our power by 1. Okay, so -2 comes down in front, decrease our power by 1. Now, for the purposes of WebAssign, for our homework, for our quizzes, for our exams, you can leave your answer exactly like this. WebAssign does not need you to rewrite this in a different form. I'll just put this part in parentheses in, just so you realize If we move that back down in the denominator, it looks like this. You do not need to take this extra step and rewrite this. It is absolutely acceptable to leave a negative exponent in your answer for our class. Any questions on this one? All right, let's do another one. How about, how do we find the derivative of square root of x? Square root of x. So the first thing we should do is rewrite the square root as an exponent. So in the chat box, tell me, square root is equal to what exponent? Square root is what exponent? Yep, 1/2, great. Okay, so I would suggest that when you're computing derivatives for this whole chapter, I would always take this extra first step, and rewrite anything that's in the denominator or anything that's a radical expression. I would rewrite that as an exponent here just to make using the power rule much easier. Once you get good at it, if you want to skip it, that's fine. But even and I've been, a math person for years and years, I still always take this step just so that I don't make any mistakes. Okay, so the square root is the 1/2 power. So our derivative here, we bring the power down in front and we decrease our power by 1. So 1/2 minus 1 is negative 1/2. For our class, you can leave your answer exactly like this. Again, I'll put in parentheses here what this is equal to, but generally we don't take this last step. So we could write this as 1 over, this negative moves us down to the denominator. So this is equivalent to 1 over 2 root x. But in general, you can just leave these negative exponents exactly as they are. There's really no reason to take either of these steps, but these are equivalent. WebAssign will accept either one. If you prefer this, that's fine. But all of these problems, I would say just don't even take the extra time to try and rewrite it. Once you get it, done, good to go. Any questions so far? How are we getting negative 1/2? So we bring the exponent down in front and then we subtract 1. 1/2 minus 1 is negative 1/2. Right, our formula was subtract 1. Yeah, so this is 1/2 minus 1. Yep, no problem. Okay, let's do one more. Let's see, if g of x is equal to 1 over the 5th root of x squared, then let's find g prime of x. Okay, so the first thing I'll do is I'll rewrite this as an exponent. So we have a square, and then the 5th root is the 1/5 power, kind of like the square root is the 1/2 power. So overall here, this is x to the negative 2/5. Right, so this 2 comes from the square, this 1/5 comes from the 5th root, and then since it's in the denominator, negative. So we apply the power rule in exactly the same way. We bring our power down in front, and we decrease our power by 1. So negative 2/5 minus 1 is negative 7/5. Okay, so that was called the power rule. That's going to be really, really, really useful to us. The next rule we have, the next two are pretty obvious. Hopefully you feel like they are. The third one is called the constant multiple rule. And this just says if we have a constant, we can just pull that constant out in front. So if C is a constant and F is a differentiable function, then the derivative of a constant times a function is equal to the constant times the derivative of the function. So we can just pull that constant out, or C times F prime of X. And I'll show you how we use that. And I would like to apologize because I got started late today. Now I'm thinking I should skip some of these proofs. So just so I can get through the rest of the material. So I'm going to skip the proof of the constant multiple, but all we do is set up the limit definition of derivative with a constant in it, and we can pull the constant out of the limit definition. Okay, so I'm going to skip that proof just for the sake of time today. I apologize. So the constant multiple rule, we can apply this really easily. So for example, if we want to find the derivative of 5x squared, the constant multiple rule says we can pull this constant out in front. So this is just equal to 5 times the derivative of x squared. We just saw that the derivative of x squared is 2x, so we have 5 times 2x, which is 10x. For our class, you certainly do not have to write out all these steps. I will for the next couple problems, and then I'll skip writing out these steps because we all know how to multiply by a constant. So in general, what I would do if I was starting with 5x squared and I was asked to compute the derivative, we know we bring the power down in front, but I still have this 5. So if I bring the power down in front, I now have 5 times 2, which is 10. And then we decrease our power by 1, so that's x to the first. We'll do one more, and again, I'll do this the long way, but you certainly don't have to write down all of these steps once you kind of get the hang of it. So let's find the derivative of 3 times x to the fourth. The constant multiple rule says I can pull the constant out in front. The derivative of x to the fourth is 4x cubed. So now we have 12x cubed. In general, you don't need to write down all these steps. So what I would do is starting over here from let's find the derivative of 3x to the fourth. I would picture I bring the power down. So 3 times 4 gives me 12x, and then I decrease my power by 1. So that's where we get the 3. Any questions on this? Okay, our fourth rule is called the sum difference rule. And it says if f and g are differentiable, then the derivative of f of x plus or minus g of x is equal to the derivative of f of x plus or minus the derivative of g of x, which is f prime of x plus or minus g prime of x. Okay, so far what we've done is just taken the derivative of a monomial, something with one term. But now, as you saw in the homework, right, and in general, we have polynomials, things with many terms. So how do we find the derivative? We just take the derivative of each of the individual terms. And again, I'm going to skip the proof, but the proof comes from the limit definition and being able to split the limit up over addition and subtraction. So I'll show you how to use this. Give you guys another second to get caught up before I switch pages, and we'll see how to use this. Let me just put a note here. This sum difference rule, sum is addition, difference is subtraction. So this rule only applies to addition and subtraction. We'll do product and quotient rule in section 3.2. So if we have a product of two functions or a quotient of two functions, if we have multiplication or division, it doesn't work out so easily. We'll address that in the next section, so we will get to that. Does anybody need more time on this page? Oh, and on a side note, somebody asked me about Stats 152 and if Grant was going to teach it in the winter. He said no, he's definitely not teaching it in the winter, but somebody should be teaching it. We just don't know who yet. It hasn't been assigned yet. So I did ask Grant about that. Okay, so let's do some examples using the sum and difference rule. And again, I hope you feel that this, just like the constant multiple rule, is pretty straightforward. So example, let's take the derivative. So again, d dx means take the derivative, find the derivative of 4x cubed minus 7x squared plus x plus 11. For these next two examples, I'll write this out the long way, and then we'll start kind of skipping these middle steps. So the sum and difference rule says that this is equal to the derivative of, we can split this derivative up over the addition and subtraction. Okay, so using the power rule, the derivative of 4x cubed, I bring the 3 down in front. So that's 12x squared minus the derivative of 7x squared, I bring the 2 down in front, 14x, decrease my power by 1, so that's to the first. And typically we don't write to the first. And then the derivative of x is just 1, and the derivative of constant is 0. Okay, so this is the extra step. In general, you don't need to write this extra step unless you really like to. What I would do is just from this point, know that the sum and difference formula says we just find the derivative of this first term, so that's 12x squared, find the derivative of the next term, derivative of the next term, and then the derivative of 11 is 0. Any questions on this one? Let's do a couple more. Sorry, got out of focus here. Somebody asked, it wouldn't be negative 2x minus 7. I'm not sure what you're referring to, but let me just go over this one briefly, really, one more time before we move on. So if I wanted to take the derivative of this term, I bring the 3 down in front. 4 times 3 gives me 12. And then I have x, and I decrease my power by 1. So instead of a 3, I have a 2. Okay, here I have the negative 7. I bring the 2 down in front. So negative 7 times 2 is negative 14. X, and then decrease my power by 1. So this is to the first power. X, this is x to the first. So I bring the 1 down in front. So that, okay, cool. All right, next one. We're asked to find the derivative of 3 over 7x cubed minus 5 over square root of x. So it is really important. I suggest you always take this first step and rewrite these. So I would start by rewriting this as 3/7 times x to the negative third. Remember, if I move this up, it gets a negative exponent. Minus 5 times x to the negative 1/2. Okay, so this one, because it's a square root, that gets a 1/2 exponent. And then because it's in the denominator, negative 1/2. So make sure you take this step. Our sum and difference rule says we can take the derivative of each of these terms. I'm going to skip writing out this middle step because we can see we just take the derivative of the first term and then add or subtract the derivative of the second term. So this first one, I bring my negative 3 down in front. So I have negative 3 times 3. So that's negative 9/7 times x to the, I decrease my power by 1. So negative 3 minus 1 gives me negative 4. Next up, I have negative 1/2. I bring that down in front. So negative 5 times negative 1/2 gives me positive 5/2. X, my new exponent is negative 1/2 minus 1, which is negative 3/2. As we've discussed in the previous problems, there's no reason to rewrite this and move them back down in the denominator. You can leave it just like that. Usually we do write these coefficients out in front, and we don't combine this x into that fraction. We would leave it like this. But WebAssign is really smart. You can write your fractions or your terms in a bunch of different ways, and it will make sure that it's equivalent to the final answer and count you correct. All right, any questions on this one? Okay, let's do some more. How about, what is the derivative of 2 square root x over x squared minus x over 4 plus the square root of 13? Okay, so much like up here where my first step was rewriting this expression in a way that makes it easy to apply the power rule, anytime you have something like this where we have a square root x over an x squared, or one term with an x and we have x down here, I would combine these exponents together. So you kind of have to go back to like remember what we did in our classes, Math 096, so sort of a algebra class where we learned on combining exponents. So here, this is x to the 1/2. And here, if we move this up, it would be x to the -2. So we have a positive 1/2 and a -2. So overall, 1/2 minus 2 gives me -3/2. So I would start by writing this as 2x to the -3/2. Okay, so all I did was add these exponents up. So 1/2 minus 2 gives me -3/2. This next term, I'm going to write this as -1/4 x to the first, just to help me apply the power rule, and then plus root 13. Okay, so applying the power rule, I take the derivative of 2x to the -3/2. I bring this down in front. So I have 2 times -3/2. The 2's cancel. That gives me -3x to the, I have to take this exponent and subtract one more. So -3/2 minus 1 is -5/2. The derivative of -1/4 x to the first, I bring the 1 down in front, so I have -1/4. Decrease my exponent by 1, so now I have x to the 0th power, which is just 1. So in general, if we have a constant times x to the first, our derivative is just the constant. The derivative of root 13 is 0. So there's our final answer. Any questions on that? Okay, let's do some more examples. How about find the first and second derivatives? Okay, so now that we've worked with this power rule on a few examples, we can do this fairly quickly. So the first derivative is given by f prime of x. And so you see this different notation. So here, this is a differentiation operator that says find the derivative. Here, this problem in words asked us to find the derivative. So if we're given a function and we're asked to find the derivative, we denote that f prime of x. Finding the derivative really quickly, right? We bring our 2 down in front, so 3 times 2 is 6, x to the first. The derivative of -2x is -2, and the derivative of a constant is 0. So there's our first derivative. Now this also asks us to find the second derivative, so we just repeat this process. So to find f double prime of x, we take the derivative of the first derivative. So we just take the derivative again. So the derivative of 6x is 6, and the derivative of -2 is 0. So our second derivative would just be 6. Now this problem doesn't ask us for the third derivative, But if you wanted to, f triple prime of x, we would take the derivative of 6, which is just 0. Now, since the third derivative is 0, any higher derivatives, the fourth derivative, the fifth derivative, those would all be 0.